So this series is something that AGRU puts on from time to time, hopefully quarterly for future. But today's topic is about ClosureTurf, effective closure of landfills and ash, sludge, and communants. So, ClosureTurf, weird science? Not at all. There are some basic forces: slope erosion protection, concentrated flow, interface shear strength, and then some not so basic: wind uplift, landfill gas pressure relief, traffic, ultraviolet longevity, and fire resistance. Today's briefing, we're going to talk about what is ClosureTurf, how does it perform, how do you work with it, design with it, on things such as infiltration equivalence. We'll look at the Help model and Giroud equations, hydrology and hydraulic design, sheet flow, concentrated flow, and peak flow attenuation, shear strength design, static and seismic, wind design, field wind stability, wind shear force versus uplift, slope hinge stability for wind design, and then some geographic considerations, and also traffic, static forces, and acceleration, deceleration, and longevity. This particular topic of interest for regulators that you may run into is just how long will it last. We'll talk about that. Fire resistance, snow loading. Not covered today, landfill gas passive and active control. That's a pretty important topic, and it deserves its own webinar, which we'll be presenting sometime in the future. So ClosureTurf, what is it? Well, a completely geosynthetic final cover system, not except for the sand. But these diagrams here on the left-hand side is a prescriptive cover with vegetated soil and topsoil over a geocomposite and textured geomembrane, pretty standard fare in the industry. Then on the right-hand side is ClosureTurf. And what you'll see is ClosureTurf can be placed right on the intermediate soil cover. We've argued that, well, both successfully and unsuccessfully, depending on the state regulator. But it really doesn't need more than 18 inches of soil cover to function. And what you do get from that is some additional airspace. It's a 50 to 60 mil linear low or high density polyethylene super Gripnet with the built-in drainage component. We call it IDS, or integrated drainage system. You can use microspike on flatter slopes. The turf itself is comprised of a 2-layer woven geotextile, which is engineered for this application, a well-graded sand infill or hydrobinder, which I'll get to a little later. And then the yarn itself, the synthetic grass, is high-density polyethylene. It does come in tan and a tan-green blend with UV stability. But if you want, you can get it in Boise State blue. UV resistance sold separately. Here's 2 basic flavors depending on topography. The IDS based is what we recommend for side slopes. It's AGRU's Super Gripnet geomembrane, which provides the integrated drainage layer beneath the turf with the sand infill, or on the top deck, it's microspike based with the turf and something called armor fill. Armor fill is basically the sand infill with a adhesive agent which prevents the sand from getting washed out. There are other applications for this. Testing indicates that armor fill may work on steeper slopes than just what we've been thinking about as far as top decks, like 5% or less. ClosureTurf, what it ain't. Sponge geometric. There's lots of resistance, but reaction by regulators to this system that it's exposed geomembrane. It isn't. And what you'll see in this presentation that the geomembrane component, the liner component of the final cover system, is protected from the environment by the ClosureTurf's engineered turf component above it, just the same as if with a soil cover. Well, let's start off with talking about infiltration. First off, with the health model. Health model has been around for many years. I remember back in the 80s. To predict leakage rate in final cover systems to generate estimates of leachate generation within the landfill. Problems with the health model as far as ClosureTurf is concerned is the primary one is the McEnroe equation that it uses. This equation is valid only when the hydraulic head lies within the thickness of the drainage layer, be that a geocomposite or gravel. It requires unconfined flow conditions. If that max head is reached, you're going to have to run another simulation considering a thicker or more permeable drainage layer to maintain unconfined flow. Second, it uses the daily average weather data. So thereby, for short duration bursts of rainfall, say the 5-minute concentration or the 5-minute intensity, it underestimates that impingement rate through the soil cover into the drainage system. So you can underestimate the head on the liner and the flow in say an underside drainage system. Now, while that second problem can be adjusted, the first, not so much as far as leakage rate calculations and flow drainage layer. Third, the freeware version is DOS. Modern Windows will need to open the installation file. There are Windows versions out there available commercially, but most of them are not supported. Good news is an Excel-based version is being developed. But again, the flow regime of ClosureTurf involves things that aren't really modelable in health, such as drainage layer flow, sand flow, and surface flow. Those all interrelate with each other. So our opinion is the health model is not well suited for ClosureTurf. So instead, we'll talk about something I call the Giroud model. It uses an infiltration model developed by J.P. Giroud and the other authors there at the bottom of the screen in a technical paper that was presented in the Geosynthetics International back in 1997, so over 20 years ago. And there you will find this equation in this particular paper, where Q is the flow through the liner, CQO is the contact quality factor, which I'll explain in a minute, H is the hydraulic head on the liner, T is the thickness of soil layer beneath the liner, D is the diameter of the liner flaw, and then K is the soil layer permeability, all in metric units as shown. There's restrictions on when and how you can use these equations, as shown here. So it does have some limitations. Here's an example of a prescriptive cover with soil over, say, geocomposite geomembrane versus ClosureTurf with prescriptive soil conditions. So as you can see here, prescriptive cover on the left-hand side of that table, got a topsoil thickness of 24 inches, a hole diameter of 1 centimeter, and the corresponding area of the hole coefficient for good contact at 0.21. This is straight out of the reference paper here, Giroud and Bonaparte back in, geez, all the way back to 1989. Good contact corresponds to a geomembrane installed with a rigorous CQA program, so producing as few wrinkles as possible on top of a lower permeability soil layer that has been adequately compacted with a smooth surface and final cover level of overburden pressure. Well, beneath the liner is an infiltration layer, which is 24 inches thick, as shown here, and then infiltration layer permeability, Q sub UM, or K sub UM, which is 1 times 10 to the minus 5 centimeters per second, or what the EPA is looking for in soil liners. And then upper permeability limits here, which work within that Giroud equation, where basically the equation upper limit on the equation where it starts to fall apart and flow goes to basically a Bernoulli type flow. So that's the prescriptive cover. Over here is ClosureTurf with 1/2 inch of topsoil, or basically the sand. Same hold conditions in the geomembrane, 24 inches of infiltration layer with that same permeability. And then here at the bottom are the flow rates, 8.7 gallons per acre per day for the prescriptive cover versus 0.2 for a ClosureTurf system. So that's our approach as far as infiltration equivalence to a prescriptive cover. It's better than, equal to, or better than the prescriptive standard, which you'll find in most regulatory language. G-flow. ClosureTurf was subjected to ASTM D6459 testing several years ago in response to, well, how's it work in rain? It was tested on a 3-to-1 slope, 40 feet long, up to 6.6 inches per hour of simulated rainfall intensity, sediment yield of only 0.03 tons per acre, much less than the standard 2 tons per acre, has a curve number of 94, and a C coefficient in the rational method of 0.76. Most of the water flows off of this system, so something you need to keep in mind. We'll touch on a little bit here. Now, for longer slopes, stormwater flow in a super Gripnet-based application of ClosureTurf has 3 regimes. IDS flow, which is represented over here by LCR. Ballast flow, which is controlled by the sand permeability, and then open surface flow on top of the system, which is controlled by hydraulic shear and open channel flow hydraulics. The distance, L sub CR, is the critical distance of the integrated drainage system matrix, or say before water level rises to the top of the integrated drainage system. L sub S1 is a transition zone where the ballast sand is saturating, controlled by sand permeability that's very short, you can neglect it. LS sub 2 is where the surface flow begins to develop, and this is controlled by the hydraulic shear capacity of the system. So, taking all that, we've solved these flow regimes for various slopes and rainfall intensities. For top deck conditions, let's generally say it's less than 5%. We can support very long slopes. So for a 100-year, 5-minute burst rainfall intensity of 6.2 inches per hour, for example here, the allowable slope length is about 900 feet. One thing in these charts is these values here, 4 through 6 inches per hour, were based on that TRI test. These higher ones you determined mathematically. Case history. Well, this is the Softly Field landfill. It was capped with ClosureTurf in 2013. It's in Pensacola, Florida, which got hammered by a huge storm back in 2014. Pensacola itself got beat up pretty bad. The storm was estimated as having a return period between 200 and 500 years. It was a beast. Based on NOAA Atlas 14 depth, duration, frequency data for Pensacola, a 5-minute intensity burst for the 200-year event would have been 16.6 inches per hour. The whole area, including this landfill, got hammered really hard. The storm only caused a 1% sand loss over the entire 23 acres of the cap, mostly around the perimeter ditch here. It took 2 guys 1 week to restore it all back in place. So this is a very durable closure system with respect to intense rainfall. Finally, regarding erosion, what stormwater runoff look like? Well, here at the Tangipahoa landfill in Louisiana, stormwater runoff from this site used to look like the jar on the right. It now looks like the jar on the left, almost drinkable. So when you're dealing with pollutant limits downstream from a landfill like this, ClosureTurf is going to help clean up your turbidity and sediment load conditions in your off-site discharge. It's very concentrated flow. This is a photo of my favorite site, Crazy Horse Landfill in California, with some HydroTurf lined downshoot channels carrying, in this particular location, about half of the site discharge. So once sheet flow becomes concentrated, that sand ballast has to be substituted with a sand cement compound, hydrobind, to create MicroDrain. This has been tested also at TRI in South Carolina with ASTM D6460. And at a 30% slope, they tested for these 5 shear levels, flow depths, flow velocities, total flow, and determined Manning's roughness coefficient, and then the max bed shear stress. Under the shear level 5, max bed shear stress got up to 15.3 TSF, with only a cumulative loss of sand ballast of 0.118 inches. We plot that readings indicates the maximum hydraulic shear is somewhere around 20 pounds per square foot. And that's at half an inch of sand loss. Base flow, the sand's been blown out. Or the hydrobinder, I should say. So minimum hydrobinder loss was measured at 10 pounds per square foot. We plug that into the shear equation here, hydraulic shear equation. This provides maximum allowable flow depths at slope like this. So anywhere from a 0.2 foot per foot slope with a max depth of 9.6 inches of water, all the way up to a 2-to-1 slope or a 1-to-1 slope at 0.5 foot per foot of almost 4 inches of flow depth. So very stout, very durable, very usable. Well, using those maximum flow depths and those measured Manning roughness coefficients, we generated these charts for you. So this gives maximum allowable flow rates for this trapezoidal channel shape that you see over on the right side for these widths here, 12 feet to 4 feet wide. So we've already done this math for you. If you got other questions, you can contact any of your sales reps within AGRU, or myself, or Watershed Geo, and we'll be happy to help you out with your site-specific issue. One thing I like about using this system is we can consolidate access benches on sites, let's say landfill, and drainage. Here I've got ClosureTurf on the side slopes, and then HydroTurf along a 10% cross slope drainage bench, access bench. So you can drive on it and it'll carry water. You don't have to build a soil section on the bench in order to cut a V-ditch at the upper slope toe, carry all that water away. You can use what you've got out there as far as intermediate soil cover and just cap it with HydroTurf, and you'll have a nice hydraulic system for concentrated flow. For peak flow attenuation, I mentioned ClosureTurf has a curve number of 94. That means high and quick peak flow, or something like the chart here. This is, again, my favorite site in California, the Crazy Horse landfill. Peak discharge into the said basin from the closed facility with ClosureTurf is up here at 160 CFS. Pre-landfill flow was estimated at 98, and using some outlet controls and some on-site detention, we got the outflow from the said basin to basically match the pre-landfill flow. The reason for that was peak discharge from this site had to match the estimated pre-landfill peak to satisfy LID, or low impact development regulations. Now there's some methods to control peak flow from prescriptive covers or on-site detention structures, like these guys here in blue. These temporarily detain stormwater on site, thus increase the time of concentration in individual subbasins up to 5 minutes, thus decreasing the peak flow. And they temporarily detain because they do, say you construct them with sacrete, they leave gaps in between the bags, and the water will drain out after the storm ends, even though it's retaining some during the peak of the storm. Other method is outlet improvements out of this brown detention pond, since it's full of sediment. And this could involve something like a spillway weir and sluice gates to temporarily increase storage during that peak flow period. However, the slowest flow is sheet flow. So ClosureTurf allows for benchless side slopes using the armor fill system. So the financial and environmental advantages of a benchless slope, and this was presented just earlier this month at the Global Waste Management Symposium, that's noted at the bottom. For the Baldwin County landfill in Georgia, they saved about $1.5 million, and this included reduction, elimination of diversion berms and downslope channels, reduction and elimination of energy dissipation devices, which are always fun to design, and hopefully they work. And then reduction and elimination of sediment storage and water quality volumes. Detention of stormwater rather than retention, allowing for smaller pond volume. And then reduction, elimination of maintenance. And elimination, potentially, of geosynthetic drainage water. So that's what this site looks like as built. And then here's its configuration as compared to the previous slide. It's all sheet flow on the slopes, down to a perimeter channel, down to a now blue detention pond because that water's pretty much clear. And the only thing they need to do is check the peak flow off the site. which is not as big a concern as it would have been otherwise with all the concentrated flow in the previous example of this figure here. Shear strength design. Well, let's start off with shear strength between turf and the integrated drainage system, or the stud layer super Gripnet. Well, maximum allowable slopes for two conditions. Construction, in which case we've got these peak and residual shear points here from direct shear testing of turf versus super Gripnet, and compare them to the 2-to-1 slope, 2.5-to-1 slope, and a 3-to-1 slope for stability. You can see equipment loads up to 5,000 PSF up here would be stable on anything below a 2.5-to-1 slope, and maybe not so much on a 2-to-1 slope. So that's where you would have to control equipment access. Post-closure conditions, well, we got some lower normal stresses down here representing, let's call it, well, just people walking across the surface for site maintenance or landfill gas well readings and inspection. As you can see here, we got a lot stronger strength at these lower normal stresses, such that even a 2-to-1 slope would be safe to traverse across doing site inspection or gas well monitoring to those that care to walk across a 2-to-1 slope. Now, super Gripnet versus soil. Again, we're going to talk peak and residual. What I've got shown here are data of super Gripnet grip side, or the spiky side, the side that bites if you hold it in your hand, versus cohesive soils in the blue diamonds and granular soils in the green triangles. Super Gripnet does a little better in granular soils simply because, well, the grips are trying to push all those grains out of the way. Cohesive soils, say a pure clay, the clay will separate around the grip and create what are called channels. So it will just channel through the clay and lose some of these shear strength. These are still really high coefficients, shear coefficients here. We got 0.65 residual and 0.90 peak for granular soil. So these are still very good shear strengths for both peak, or for both cohesive and granular soils. Residual wise, still granular soils do a little bit better. These are still really high X coefficients though, or shear coefficients. So very strong, can stay stable in all manner of conditions. And again, here I've got the 2-to-1, 2.5, 3-to-1 slope on these charts, so you can see where this stuff lands. Say on a 2-to-1 slope, you're going to want to make sure it's a granular soil that you're placing super Gripnet on versus a cohesive soil. But even cohesive soils, you've got stability with a factor of safety of 1.5 on 2.5-to-1 and 3-to-1 slopes here. For a MicroDrain or microspike on these same slopes, generally you're probably okay with even a 2-to-1 slope for peak, even though this 2-to-1 slope is landing right along the linear regression line of these data points. Those of you who talked to me before know I recommend using this line here, which is the 90th, lower 90th confidence interval and stability, which would allow placement of 2.5-to-1 and 3-to-1 slopes of this material on soils. Here is residual starting to get a little more, or the linear regression line is approaching the 2.5 to 1 and the 3 to 1 slopes. So again, this is something you want to consider on a site-specific basis. You want to know what that site soil is going to do against microspike or any texture geomembrane for that matter. Let's go on to wind design. Now, biggest concern that we initially ran into from regulators was that ClosureTurf was an exposed hybrid geomembrane, which means it's susceptible to wind damage. Not so. Now, while wind is death, or can be death for exposed geomembranes, it's not so for ClosureTurf because it did something very odd when they tested it in the wind tunnel. As it started to uplift, pressure started to rise, so it was being picked up by the wind, and then peaked here at about 70 feet per second, and now it's declining. So it's actually going negative. You see the turf blades here being pushed down by the wind. They're acting like a spring and pushing the whole system down in this situation. And this is true all the way up to wind speeds of 170, 175 feet per second. That's a Category 3 hurricane wind speed. Even Katrina, when it hit New Orleans, was Category 3. So this is a very stout system when it comes to, hurricanes, hurricane wind speeds. So how do you design with it? Well, surprise, surprise, shear governs like almost everything else versus wind uplift. As you saw in the wind tunnel video, normal loading was a maximum of 0.1 PSF at 70 feet per second. So not a lot of uplift. But using that tunnel data and applying a factor of safety in this equation here, where tau is the measured shear force, D, turf, is the interface shear angle, residual, and then P is the wind loading normal force, which shows either positive or negative. And here's what we get. This is an edge or hinge condition, say at a top of slope to a side slope. Here's an interior condition across either top deck or one of the side slopes, middle of the side slopes. We plug in this wind speed, 115 miles per hour, run up to the top of the blue curve for the hinge condition, and we need 10 pounds of sand, 10 pounds per square foot of sand ballast along that hinge. Here in the interior condition, we only need about 1 3/4 pounds. Beauty of it is at our minimum sand ballast depth of 1/2 inch, you're going to get 4.5 pounds. So the interior condition is always going to be stable, and you need to concentrate your ballasting design on edge or hinge conditions. Now, texture geomembrane microspike needs a little bit more sand, up to 14 pounds per square foot along hinge or top of slope conditions, and then the 4.5 half-inch thick sand layer is still sufficient for interior or field conditions under these same conditions at wind speed 115 miles per hour. So where is wind design concerned? Well, this was my previous example site here. It's up in the Sierra Mountains of California. They get some really gnarly winds there, up to 115 miles per hour. Here in hurricane country, you're going to get similar wind speeds, higher wind speeds, but as shown previously, in the wind tunnel testing, ClosureTurf can resist Category 3 hurricane wind speeds, which you're going to find in the interior where most of these sites are anyway. Traffic. Well, usual question is, can I drive on it? Yes. Not like this, but yes, you can drive on it. Using equations from Kerner, we can demonstrate allowable vehicle stresses on the system. And Kerner, I mean, his textbook, Designing with Geosynthetics, which has a 6th edition out right now. And considering a light vehicle pickup, which landfill gas monitoring crew might use or site inspection will use, we assume the tire pressure here of 45 pounds, which is kind of high for a pickup, or a heavy vehicle fire department water tender with tire pressure of 120 pounds per square inch. Mechanics of traffic loading consist of burst resistance or bursting pressure through the IDS system here. The geotextile bursting through that gaps in between the studs, tensile strength of the geotextile components of the turf, puncture resistance or punching through the stud layers, puncture resistance of the geomembrane itself from, say, rocks or whatever underneath, and then braiding. Now, these equations, it would take a little bit of time to go through them. In this one-on-one presentation, I'm just kind of touching on what those considerations are. That is a other webinar that I've actually done previously, and we will do again in the future. But let's go to one of the hot button items, and that's longevity. How long will this system last? Well, the Geosynthetic Research Institute, GRI, that's both Bob and George Kerner, have been testing, exposing various geomembranes to ultraviolet radiation in their laboratories for a lot of years now. And they've determined that high-density polyethylene has the highest UV resistance at an estimated half-life of 50 years. Based on their preliminary results, they've got some more results nowadays, but at the time of these reports, it was about 50 years. And what do they mean by half-life? Well, that's 50% retained tensile strength or elongation property. Is that end of life? Well, that depends on use, and it's not necessarily end of life, as we'll see in a minute here. First, a little bit about solar ultraviolet radiation. Common denominator between field and lab data is not time of exposure, but rather level, or in this case, where. To control variables, laboratory testing is conducted at a constant temperature with a nominal 40-watt UV bulb, 20 hours a day per ASTM D7238. What that means is that 40 watts of UV, that's high noon on the summer solstice at the Tropic of Cancer, as shown here, or December 22nd at the Tropic of Capricorn for the Southern Hemisphere. So about an hour, one day out of the year, is when this exposure actually happens on a clear day. So where UV exposure in the most critical wavelengths, where it occurs doesn't matter as much as when it occurs. So here in the Northern Hemisphere, we've got UV levels, irradiance levels lower here in December than they are here in June, to the point where some of these critical wavelengths don't even always show up in December. So the light bulb that they use in the lab, it's a UVA 340 lamp produced by Q Labs, and it simulates solar radiation pretty dang well up to a wavelength of about 340 nanometers. You'll see the critical wavelength of polyethylene where the UV radiation gets into the structure of the polyethylene resin and starts to break it down, is say less than about 305, wavelength 305. Polypropylene is up here somewhere, which tends to explain why polyethylene does pretty well on the UV exposure. So how about solar irradiation versus geographic location? The Atlas Weather Servicing Group test location north of Phoenix is probably the hottest in the United States, continental United States. Well, actually the entire United States for UV and temperature. That's the critical combination. They had turf samples sitting at a direct exposure 45 degrees south, using and monitoring and controlling the measurements using these ASTM methods, and had 4 exposure durations: 1.3 years, 5 years, 7 years, 10 years. Now, taking that data, made this is called an Arrhenius plot. More detail on this in another webinar, but just for the basics here. We had these 4 points, 1.3 years, 5 years, 7 years. These were the measured retained tensile strengths. So using the last 3 are these green triangles. I'm going to call that stage C degradation. This point here at 1.3 years, either stage A or stage B. And it's a detailed topic. There's more on that in the other webinar. But using these last 3 data points, half-life can be predicted as being reached in 215 years. Now, using Atlas's solar radiation data and temperature data, the entire time these samples were being exposed at their facility there north of Phoenix, and then plugging those values into the GRI Report 44 methodology, it predicted a half-life of 106 years. Now, in a situation like this is frankly excellent correlation. It's within an order of magnitude difference. So this is pretty much agreement. When you consider the minimum strength required in the turf component to hold the whole system together, the sand ballast and the geotextile and turf and all that, we're talking a longevity that's on the order of centuries. I mean, till end of life is basically centuries. So, long time. How about elsewhere? Well, we've got data, we've got field data here in somewhere around Phoenix, Arizona, but there's all kinds of other data that's been collected all around the country. That's called Typical Meteorological Year, or TMY3 data, from the National Renewable Energy Laboratory. So comparing that to the Atlas climatic data for that test period that the turf was out there at their facility, and using the baseline laboratory data, we can make some predictions all across the country of what's going to happen with ClosureTurf based on these recorded data stations that was used to produce this map that you saw before. So again, worst parts of the country right here in the southwest for UV and heat exposure, and basis of the longevity prediction made here. Longevity will be a lot longer, a lot better elsewhere across the country than where it's been actually tested. A little bit about fire resistance. Don't really have any design calculations to show you here, just some observations based on this investigation. Did some testing using this ASTM method, which is meant for composite roofs for fire resistance, and basically a burning brand test using 3 different brand sizes, Class A, B, and C. Class A is 12 inches by 12 inches, B was 6 inches by 6 inches, and C was essentially a 2 by 2 cut into a square. Here are the brands themselves, made out of 1 by 1 finished pine stock, and a 1.5 inch long piece of 2 by 2 pine stock with saw curves on opposite sides according to per the ASTM specifications. So, lit these babies up in my Weber barbecue when my wife was safely out of town, and let that Class A brand, 12 inches by 12 inches, burn with an open flame for 30 minutes. The Class B brand, not quite as long, and the Class C brand, even shorter still. Allowed those to smolder overnight. Make sure everything was out before I started poking around. And then took these measurements. Here on the left-hand side, you see the Super Gripnet geomembrane that was underneath the Class A brand. Basically, a melt zone on the Super Gripnet was 12 inches by 12 inches, or the size of the brand itself. The Class B brand actually had a melt zone a little larger than itself, about 1 inch, so 7 inches by 7 inches versus the brand size of 6 by 6. And the Class C didn't even melt through the turf. So what was found here is none of the fires broke through the geomembrane. It didn't burn through the Super Gripnet. It melted it, but it didn't burn it. And more, the fire did not propagate away from the brands themselves. Some of the turf tips around the brands got melted, but fire did not spread. So if a burning tree branch or what have you falls onto, say, the perimeter of a ClosureTurf facility during a wildfire, you'll have some localized, easily repairable damage versus losing the entire vegetated surface, in which case a raging fire going up the side slopes will burn up landfill gas wells, landfill gas piping, and any other monitoring or environmental controls that you might have the surface on your site. Not so with ClosureTurf. Snow loading. Well, here's some examples. First off, here's Hartford, Connecticut. They actually have solar panels installed on this site, which aren't doing much in this picture right here, but they're there. And then here's Portola, California. This is in the northern Sierra Mountains. This middle photo, you'll see an extent of hydroturf running down the slope to this detention basin here. And then more hydroturf around the perimeter of the slope, also dropping into this detention basin. The rest of it is all ClosureTurf that was using an on-site sand. So what happens when ClosureTurf freezes? Well, based on these existing installations, which are more than just Hartford, Connecticut, and Portola, not a lot. For landfills, the internal heat seems to keep the drainage matrix, the IDS matrix, clear. For non-landfills, there's a frequently asked question: does ice form in the IDS stud area here and push the turf away from the IDS studs? Hence, you lose shear interface and shear strength. Well, the critical time would be when the ice melts down through the turf sand to the top of the studs, like so that you've got a layer of ice here that the turf is sitting on. Now, presuming the turf is raised above and is sitting on that ice, tension would develop in the woven geotextile of the turf, like so. From wide width tensile testing of the turf, you can determine how large T can be. So let's use a 10% strain, and the developed tensile force in the woven geotextile was an average of 680 pounds per foot. Still in an elastic regime here. When the tensile force is released, it might have some residual strain left, but overall that should be repeatable. Now, as far as driving forces down the slope, let's assume a snowbank is sitting on top of the turf. Melts during the day, freezes at night. Snow weighs about a third of that of water, so a 4-foot deep bank would place about 80 pounds per square foot on the, say, the turf ice interface. So for a 3-to-1 slope, the driving force would be 27 pounds per square foot at the bottom of the turf sitting on the ice. For a 2-to-1 slope, that would be 38 pounds per square foot. So if T allowable is 680 pounds per foot, then that driving force can only be applied over a slope length of 25 to 18 feet, respectively. Well, no one builds slopes that short, so that's pretty much a yikes. So why aren't snow-loaded ClosureTurf's slopes, why aren't they failing? According to this, they should, but they're not. Well, the freeze-thaw cycle of snow depends on a lot of variables. Net incoming solar radiation. Snow has an albedo of 0.4 to 0.8, depending on old, aka dirty, to new, nice white powder, skiable powder snow. There's heat from the air during the diurnal temperature cycle. There's terrestrial irradiation emitted by the clouds and sky, absorbed and reflected infrared. Heat transfer from the ground, landfills are higher than non-landfills in this case. Latent heat of evaporation, so when the snow or the moisture in the snow sublimes into the atmosphere, it leaves behind heat. And then there's heat transfer by falling rain. Well, all of these, the constant is this one. Heat and cold during the day and night. And what happens is as the air temperature above the snow drops, the snow at 0 degrees Celsius will then drop to match that air temperature, and that cold wave, if you will proceed downward through the sand, turf sand mixture down to the interface below with the super Gripnet. So this area here, for the most part, is going to be at 0 degrees centigrade until this really, really cold up here from the air can transmit its way down. So what happens is the water in that IDS matrix will run off, it'll be dry. So there's always going to be contact between the IDS studs and the bottom of the turf, hence static stability. That's my explanation as to why these systems don't fail in the presence of snow load. They're just, ice is not an issue. And that concludes today's presentation. For those of you needing professional development hour credit, we can offer that in these states. We cannot offer it in Oklahoma, Louisiana, Florida, and New York because those states have special requirements as far as presentation or PDH hours. They have to be blessed in those states. Anyway, we can't offer it in those states. If you have licensure in some of these other states, give us a shout, give us an email, give us a call, and we'll get you a PDH cert for that state. And you can reach me at either this email address or that phone number. And I'm going to leave that up and unmute everybody. And if you got questions, please let me know or call them out here or send me an email. So, any questions? Not hearing any. And I'm not seeing any showing up in the chat. So we'll sign off here. If you have any questions at all, or you need a PDH search, get a hold of me or the organizer, Cody Miles, and we'll get you taken care of. So anyway, that's the end of the presentation. Yes? Okay. We'll see you next time. All right, thank you.